Good morning, ladies and gentlemen. I want to talk about demand and perspectives on mechanized tunneling technology. I structured the lecture as follows. First, want to talk about the demand of underground infrastructure systems. Before, I want to talk about the motivation for more and more use of large diameters of tunnels, and focus then on different types of tunneling machines. Also addressing the tendency of the tunneling projects of today. Before, I want to give you an overview about some international case studies in both soft ground and hard rock TBMs, and conclude with an outlook. Due to the increasing population and urbanization, there's still a big demand for underground infrastructure systems. This mainly focusing also on utility tunneling, but also on traffic tunneling, such as road, metro, or rail projects. The motivation for large diameter tunnels, the trend is to have large diameter profiles, mainly for road tunnels, to integrate more than 2 lanes of traffic in the profile. Or to have a multiple purpose use of the tunnel profile to integrate here not only the road but also metro line, or like a project that was realized in Kuala Lumpur with a stormwater road and management tunnel, where the double deck is used for road traffic, and in the rainy season in Malaysia the tunnel is closed for traffic and will be used to release the stormwater. Then the challenges in mechanized tunneling depends strongly on where the project is realized. If we talk about urban tunneling projects, then you have mainly to underpass sensible structures with low cover. And here settlement controlled operation process is essential. Also, a demand or challenge are more and more variable geological conditions. Also, when you cross through mountain ranges, we have long tunnel drives to deal with, or also when underpassing under subseas or rivers. There's also demand not only of long tunnel drives, but also to cope with high hydrostatic pressures, and this combined more and more with larger tunnel profiles. So there are different types of tunneling machines available dependent on the specific project conditions that will be faced along the tunnel alignment. I don't go into details. You have here the 2 soft ground machines, earth pressure balance shields and mix shields with a slurry supported tunnel phase. And then you have, if you are operating in hard rock conditions, you can have gripper TBMs, single shielded hard rock TBMs, or double shields. Or to cope with high variable geology, you can have so-called multi-mode machines. These multi-mode machines can change its operation mode in the tunnel relatively quickly within a short time. So the multi-mode machines had been mainly designed based on conditions where you have long stretches in soft ground beneath the groundwater table, sections in hard rock, or even here if you have to cope with highly variable, highly permeable ground conditions beneath the groundwater table, also incorporating karstic features. So the tendency of tunneling projects of today. I have some references here. Today there are worldwide a lot of projects, so-called mega projects, that have to be dealt with, and the realization of these projects have to be done within a quite tight time schedule. So in the in Great Britain, the Crossrail project was realized. This incorporates more than 118 kilometers of tunnel. Of these 118 kilometers, 42 kilometers had been built beneath the surface with the use of in total 8 tunnel boring machines. Then over in Malaysia, in Kuala Lumpur, they built in total 3 new metro lines. The first metro line had an underground section of 9.8 kilometers, where they also used in total 8 machines. And also Doha Metro, the project will be finished soon. That means the tunneling drive will be finished within the next months. Here, 100 kilometers of new metro lines is built with a total number of 21 machines that operated in Doha. At the moment, there's still 2 machines left. One will finish end of this month, and the last machine will finish operation next month. So the tendency for tunneling projects of today is to focus also on factors for safe and successful project implementation in time. Such mega projects are under tight time schedule, and the guarantee that these are realized in time is generally if there's political interest involved and also support from the people and the environment. Then it's important also that you have a close partnership with all parties involved in a tunneling project, incorporating the clients with its designers, but also the contractors, and finally support by the machine manufacturers. This can also be done with optimum adaptation to the project conditions. Relevant for the realization of such mega projects is also that you have operative performance. This means that you have qualified contractors that know what to do to realize these partially quite challenging underground projects, or also it's supported by so-called also package and managed solutions that are offered by the suppliers, and that they not only deliver the machine, so we also deliver additional equipment and related services, but also training modules to guarantee that the project is taken successfully to the end. The projects also, there's quite strong involvement of tunnel boring machines these days in all underground infrastructure systems. This is also because with the development of the machines, they can cope with quite challenging geological conditions today, with the flexibility of multi-mode machines or variable density machines. Even challenging projects can be realized reliably and in time, and what is essential with safety, also in respect of settlement operation process, especially when we are talking about urban tunneling. Then the safety of operation, it's also a relevant factor for increased use of TBMs, because here you can have less impact to the environment, and you can also plan the project, and the time schedule is generally kept within the planned time. One project I want to highlight is a project in Kuala Lumpur for the first metro line that was built. It comprises a 9.8 kilometer long underground section. The geology is quite complex in the city center of Kuala Lumpur. Here they have mainly Kuala Lumpur limestone. This is characterized by karstic features, and then they have alluvial soils like clays silts. But for tunneling, these karstic feature limestone is quite demanding. In the past, mixed shields had been operating there and faced, due to hollow spaces, there was a loss of bentonite that led to blowouts and settlements on surface. And based on the experience in the past, we developed, especially for such conditions, a new type of machine that incorporates here the advantages of an earth pressure balanced shield and the slurry shields, here with a variable density machine. The machines have a small diameter, typically diameters for metro tunnels in the range of 6.6 meters of excavation diameter. And the machine can be operated in different modes, in a earth pressure balanced mode, in a closed slurry mode, but also in a high density mode. And then we talk about materials with a density of up to 1.7 tons per cubic meters that are handled with the machine and the related logistical system. To address also quite challenging project that was realized already end of the 90s in Germany is the Forst-Tube-Elbe tunnel. It's a 2.6 kilometer long road tunnel underpassing here the river Elbe in Hamburg. It was built next to 3 existing immersed tunnel tubes, but because this here is a frequented shipping lane, the only alternative to build a connection was here to use a shielded tunnel boring machine. The geology was highly variable, comprised abrasive sands, clays, glacial drift formations, with boulders inclusions in the diameter range of up to 2 meters, and here high hydrostatic pressures of up to 5.5 bar. So therefore, we had to design a machine that could safely excavate and line the tunnel. These boulders, they had been addressed by installing here a stone crusher in the mix shield to crush down the boulders to a transportable size, thus that you can hydraulically convey the material. But the machine was also equipped with a seismic soft ground probing system. That's a system where you have sender and the receiver installed here in the cutting wheel. They send out seismic waves in the ground, and through here the density reflections, they are recorded. The software, we have a 3D software so that we can illustrate possible boulders or natural obstacles, so that the machine driver knows what is expected about 40 meters ahead of the tunnel face and can adjust its operation and the advancement speed in order to avoid possible damage. Well, specific for that project was also due to the high hydrostatic pressures of up to 5.5 bar to look for a safe way to change the tools. So that's why we designed here the 5 main arms of the cutting wheel accessible in atmospheric conditions. This system was also used for follow-on jobs, like in China, where we had 2 machines for long tunnel drives. The 2 machines underpassed here the Yangtze River to connect the mainland of Pudong in Shanghai with an island. Now the question is, why did they use here a tunnel and not a bridge? That was here they had, it's also shipping lane frequented, and here you have the harbor of Shanghai. So to not interfere with the ship traffic, it was the only solution to use a shielded tunnel boring machine. The project here I want to talk about now is a project that was finished last year. It's one of the most challenging projects that was realized up to now. It's crossing beneath the Bosporus Strait in Istanbul in Turkey. The geology is quite complex. Here sandstone, mudstone formation, that's full phase hard rock, then transition zones, mixed phase conditions of rock and soil. And here at the deepest point of the crossing, soft ground, and this related with high pressures of up to 13 bars, where the machine was designed for. The tunnel is a road tunnel for light vehicles. It carries 2 lanes of traffic on 2 decks. The tunnel is lined with reinforced concrete elements and have an inner diameter of 12 meters. The machine was a 13.7 meter mix shield. It was specially designed to cope with the demands of the subsurface conditions and also to cope with the high hydrostatic pressures. Here also the cutting wheel comprised 6 main arms and 6 side arms. The main arms were designed also with the system to be accessible in free air to change the complete set of tools here on the main arms. The cutter head features here. Due to the mixed phase conditions, it was stressed with disc cutters and soft ground tools. We installed 19-inch disc cutters, strong wear protection plates due to abrasive nature of the subsurface conditions. Here also sectorized wear levels to detect possible damage to the cutting wheel structure. And also each single disc cutter here was equipped with a system to detect if the disc cutter is rotating and also to measure the temperature of the discs. That's an illustration to look in one of the main arms for atmospheric tool change. The water that you see here, it's not from the front. It was just used to clean here the housing of the disc cutter. So all work here in that arm is done in free air condition. Therefore, each single tool is installed in a small airlock. That was first time used in Hamburg. That's the original cutter head here. That's now part of a museum in Hamburg. So with this design, it's possible to do non-expansion maintenance. Here also the illustrations of the tool exchange in that conditions in free air. It looks relatively like you have enough space, but the picture was taken with a wide angle lens, so it's not that much space available. It's relatively confined area. Here the system of monitoring of the disc cutters. Like I mentioned, each single tool is equipped with a disc cutter rotation monitoring system, measuring if the disc cutter is rotating and measuring also the temperature. Now we have further developed the system also to measure the load of the disc cutters. So the information is sent to the operator's cabin, and here the machine driver can strongly monitor if one of the disc cutters is blocked. And here the red circle, it's the center disc cutter with the red color. It indicates that this cutter is blocked and that you have to enter the chamber now for tool change. But because you always have to design the machine with a redundant system in case that this system with accessible cutting wheel in free air would fail, or for other maintenance issue under quite high pressures of up to 13 bar, you have to design the machine that you can send divers in under saturation to do here some maintenance or repair work in the pressurized chamber area. So the machine foresees here, and you have, when we talk about such high pressures, it's and saturation diving, you have to have pressurized habitat on surface and also a transfer shuttle for this crew. For the crew, and so you need to guarantee that the line to the front to attach here the transport shuttle is free at any time. That's an overview about the actually faced pressures during the machine operation. The machine was designed for 13 bars, and you see that for the majority of the tunneling, the pressure was well above 6 bar, and we faced maximum phase pressures of up to 11 bar. That was the breakthrough of the machine then finally in August last year. Another project quite challenging is a project that is currently in operation in Hong Kong. It's for 2 parallel subsea tunnels that will connect here Tuen Mun, that's the mainland here, with the airport area. The tunnels will have a length of 4.2 kilometers, twin bore tunnels, and in total there's 3 machines used. One machine is up to now the world's largest machine. It already finished its tunneling section. It has a machine diameter of 17.6 meters. The tunneling conditions here also quite challenging. Mixed phase conditions, full phase soil, full phase mixed phase conditions of solid rock conditions, granite. Granite is a rock of high strength and abrasiveness. And then this related with also high hydrostatic pressures of up to 5 bar. That's the machine, the 17.6 meter machine that was here factory accepted. And in parallel, you see here a small diameter machine. It looks like a micro tunneling machine, but that's a 6 meter machine, typical diameter for metro tunneling. Also, that machine was equipped with machine design features to be able to do hyperbaric interventions and to cope with pressures of up to 5 bar. These are some illustrations about the assembly. The shaft was near to the harbor side, so it was easy transporting the machine on site and for also assembly in the shaft. Also here view on the tunnel and here on the backup structure. Another project to highlight is a job that was done in St. Petersburg in Russia. St. Petersburg is a swamp area characterized on the surface through quite soft clay formations, and in the crater depths you have the stiff clay formation, which is good for any foundations. There are a number of metro lines, and there are 3 stations, underground stations, that are not accessed from surface. And so there had to be done 3 shafts, mainly for the use of escalators, to give a way down to the station area. In the past, these escalator shafts were constructed using conventional methods. They used the freezing technology related with excavators. But because when they had to defrost the soil body, they had settlements in the range of up to locally 0.5 meter. So they looked for a more safer concept to address the point of settlement controlled operation, but also to reduce the time to excavate these shafts. So that's how we came in with the design of an earth pressure balance shield. The tunneling drives had been only relatively short, between 100 up to 140 meters. That's a relatively short tunneling length for the application of a tunnel boring machine. But here the demand was also to drive down these shafts here with a decline of 30 degrees. That's quite steep. You see here the machine in position when operating here in a 30-degree decline drive. The demand of tunneling was here, first of all, the decline of 30 degrees, the short tunneling lengths, tunneling in urban area, but also the demand to recover the machine. After it finished the first shaft, it had to be retracted to be furnished for the second and third drive. The machine, when you operate in a decline of 30 degrees, you have here the heaviest part of the machine with the main drive, and normally with such a decline drive, the machine would tend to sink down. You have to keep it into its position. That's why we used here tension ropes on the left and right hand side and tensioned the machine from the shield to the shaft construction to keep it into its alignment. Another demand was to recover the shield after the first and second drive. That's why we designed the machine with an inner shield shell and an outer shield shell. And after the first drive, that outer shield shell was left in the shaft as part of the shaft construction, and all the inner body could be retracted. For the second and third drive, the machine was then equipped with a new outer shield shell. You see here, that's the finish down at the station level, and afterwards the machine was disassembled and retracted. Focus also here on very large diameter tunneling drives. Here a project that was realized in Italy between Bologna and Florence. It was a 3-lane road tunnel that was built, 2 parallel tunnels of 2.5 kilometers. Here the demand was mainly the prevailing geological conditions, comprising mudstone formations and clay. But here the special demand was that along the entire tunneling profile, methane gas was present. So that's quite challenging for the machine operation. The contractors used an earth pressure balance shield, and it was demanded to drive the machine along the entire section in a complete closed mode operation. That means the chamber in the front completely filled with material to avoid the exposure here of methane gas in the chamber. Then the next demand was to extract the muck. Normally here you have an open system, but because you have people here working and the danger of also methane gas exposure, we designed an 80-meter long conveyor belt completely en-housed in a double shell wall that was strongly ventilated inside and outside. And then at the handover to the tunnel belt conveyor, we had a strong ventilation system. So here also you didn't have people working in the tunneling section. One of the last projects I want to present is here the longest rail tunnel that was built in Switzerland to connect here the Italian side with the Swiss side here, underpassing the Gotthard Massif. Quite challenging project. These are 2 single-track rail tunnels of 57 kilometers. About 85 kilometers were excavated using 4 tunnel boring machines of Gripper TBM type. The 2 machines here started on the Italian side in the south, excavated about 14 kilometers. Then the diameter was enlarged for the remaining about 11 kilometers. From the northern side, 2 machines started for about 11 kilometers. They were also reused for another about 7 kilometers. And the central part here was done by drill and blast. This mainly due to high convergences in that area. But for the tunneling drives, that section was quite demanding with overburden of up to 2,100 meters, where they also had to cope with convergences. So the machines had to be designed for that. That's the overall timeline of the Gotthard Base Tunnel project. The tunneling started with the machines in 2003. The complete tunneling works were finished in 2011, and in June this year, the tunnel was taken or was commissioned and taken in operation. That's the final breakthrough. The machines had been pure hard rock machines, equipped with disc cutters, strong wear protection, and they achieved in good rock formations performances up to 56 meters. But here it's more challenging also to cope with the long tunneling lengths. And here it's not only the machine drive that is a challenge, it's also the logistic that is related with the tunneling. This tunnel, here you have, because it's a twin rail tunnel, every 325 meters, cross passages were built. And here challenges with also high rock overburden. You see that 80% of the complete tunnel were excavated using machines, and 20% drill and blast work was involved. So the last project I want to highlight, I think it's also quite a fascinating project. It's for a hydropower project that was realized in Switzerland in remote area. Here 2 pressure shafts of only 1 kilometer each had to be built, and that in a height of up to 2,100 meters. You have here down the base valley camp, and the challenges of the project had been the remote location in alpine area, and also the challenge was to deal with gradients of 85%. So the machines had to drive upwards, and after the first tunnel was built, it was retracted through the already built tunnel and finished the second tunnel. The geology was also quite demanding. It was limestone formation, normally ideal tunneling formation, but there was a karstic feature predicted approximately at the half of the tunnel alignment, but nobody exactly know what will be faced in that situation. We supplied a 5.2 meter gripper TBM to cope also with the steep gradients. You see here the machine in the angle here of 40 degrees. It was equipped here with gripper blades to have rebound, then also with 2 safety recoil systems at the rear in case that one system fails. So these 2 systems work independently from each other because you want to avoid a slipping back of the machine in that high gradient. That's, the logistic was also challenged due to the remote area. The base valley camp is at a height of 800 meters above sea level. The job site at 1,800 up to 2,100 meters. So all equipment was transported here at the base valley camp through cable car system up into the remote area. That means here, that's the center part of the cutter head. All trucks, all people, all had to be handled here through that cable car system. Up in the mountain, there was an assembly cavern. In that assembly cavern, we did an assembly of the machine in a horizontal direction here on a steel ramp. The machine was then pushed through a starter tunnel and started right away excavating in a 150-meter vertical curve radius. You see here the picture of the start-up position here of the machine. It then excavated, and after about 550 meters, the machine faced the fault zone, and the fault zone was characterized by more a loamy matrix, and so they looked of how to stabilizing that zone. They wanted to do a pipe injection umbrella, but the geology was non-injectable. And so we had to look for a solution to cope with that only 30-meter long stretch of that fault zone. It put a delay of 6 months in the program, but we could handle it. We installed 360 degrees behind the gripper shield here, steel liner plates, and also some pushed cylinders to push the machine through that zone. The machine then successfully broke through, but then the demand was to bring the machine back through the already excavated tunnel. So we disassembled the 4 outer parts of the cutting wheel, retracted the machines in steps of 10 meters, and then the machine was furnished and started excavation for the second tunnel. That's then the final breakthrough. And you hardly have a picture where the people can sit on the cutter head. So this shows you exactly how steep gradients had been handled in that situation. The tunnel is now already in operation for the hydropower project in Switzerland. To conclude, you see the different applications of tunnel boring machines, different geologies, different diameters that are handled. And you always have to look for tailored equipment, but this with utmost focus here on the safety of operation. And also what is quite important is that you have a strong involvement of all parties involved in the tunneling works. And that's finally then the benefit of the project if the client, contractors, planners, and also the machine manufacturers works hand in hand. With this, I'm at the end of my presentation and want to thank you for your attention.